Hello, everyone, and welcome back. So today what we are going to do is, before moving on to beams and frames, we're going to talk about an important concept, and that is related to stability of structural systems. And actually, all the concepts that we are going to talk today are equally applicable to truss systems or like frames. So these are like very general concepts. And I hope that it will also help you to understand structural systems in a better way. So let's get started. So the main idea is as follows. The stability of the structural system is actually closely associated with the eigenvalue problem. And if you recall from your linear algebra class, like a long time back, uh, eigenvalue problem is a very fundamental problem in algebra or in linear algebra. So in this case, we are going to state the eigenvalue problem like this. So we are assuming that there is a stiffness matrix or there is a symmetric matrix. I should not say a stiffness matrix in this case, a symmetric matrix that is given to us. And this is like size n by n. So this is, I'm calling it a. I am assuming this is a symmetric matrix. And this is an important assumption. We will not go into the theory of eigenvalue and how these are solved, but I just want to give you an overall statement on and how this works out. So we are assuming, starting with the symmetric matrix, we want to find a vector v and a scalar lambda such that this relationship is satisfied. So what we are saying that a times v should be equal to lambda times v. So, oh, sorry, there is a typo here. This should be n by 1. I will fix it later on. So this is like what we are trying to do is we are multiplying a matrix and a vector, and we are saying the solution, the multiplication should result in lambda times the vector itself. Again, this is a typo, so I will fix it in the slides. So if we are able to find a scalar and a vector v that satisfies this relationship here, we call this v as an eigenvector, and sometimes we also call it an eigenmode. So it depends on the whichever terminology you are familiar with. And lambdas, we are going to call this number or a scalar as the eigenvalue. So without going into the detail about like how do we calculate these things and what are the mathematical properties of these numbers, we really don't care about this in our class right now. So the idea is, in our class we are going to use this function EIG. So this is an inbuilt function in MATLAB that can calculate eigenvalues and eigenvectors for us. The theory is very involved, so again, I don't want to go into the theory of eigenvalues and eigenvectors. If you end up going to the graduate school, you will learn these concepts maybe later in your classes. So this MATLAB function EIG outputs two things. It outputs a matrix V and a matrix D, so two variables. So here V is a matrix of size n by n, and the columns of this matrix are actually the eigenvectors or eigenmodes. So we'll look at it in a moment. And similarly, D is a diagonal matrix. Diagonal matrix means the off-diagonal entries are 0. And the diagonal entries are actually the eigenvalues. So we can easily calculate eigenvalues and eigenvectors of a matrix using this command in MATLAB. So again, we can think like that V is composed of n columns. So V1 is the first column, V2 is the second column, and Vn is the nth column of this V n by n matrix. And as I told you earlier, these are diagonal matrix. So you can see that off-diagonal entries are 0, and the diagonal values are all, I'm labeling them as lambda 1, lambda 2, lambda n. And each of these pairs, so let's say V1, lambda 1, V2, lambda 2, these are eigenpairs. For example, we can choose any of them and we can write something like this. We can say that A times Vk is equal to lambda k times Vk. So this is actually the eigenvalue problem, and these eigenvalues and eigenvectors satisfies the statement of eigenvalue problem. So this is the solution of the eigenvalue problem. And so you can see very carefully, if you think very carefully, for a matrix of size n by n, you will have n eigenvalues and n eigenvectors, okay? And they go in pairs. So v1 corresponds to lambda 1, v2 corresponds to lambda 2, and vn corresponds to lambda n. So just be careful when you associate these pairs together. And in MATLAB, they are already arranged for you in the right way. So you choose the first eigenvalue and the first eigenvector. That's the eigenpair. So typically we call this lambda and v as the eigenpair. And for a matrix of size n by n, there are n eigenpairs. And actually, if we know the eigenvalues of a system, we can associate the stability of the system with the eigenvalues. And the ideas are as follows. So what we have to look at, we have to look at the eigenvalue of the stiffness matrix, or precisely the KFF part of the stiffness matrix. So in this case, I'm assuming that lambda 1, lambda 2, up to lambda n are the eigenvalues of KFF part, okay? So we are not looking at the global stiffness matrix, like the entire stiffness matrix, but just the KFF part of the stiffness matrix. And then we are going to say that the system is stable if all the eigenvalues of KFF are greater than 0. So it means that lambda 1, lambda 2, up to lambda n, everything has to be greater than 0. And if you recall some of your linear algebra, I don't know how much linear algebra you remember, but there's an important result in linear algebra. The determinant of KFF is actually the multiplication of all the eigenvalues. So determinant of KFF can be calculated by lambda 1 times lambda 2 times lambda n. So if you think very carefully, if any of the eigenvalue is 0, then determinant of KFF is 0. And then KFF is not invertible. So you can see that stability is actually closely also related to the invertibility of KFF. So if any of the eigenvalue is going to be 0, the KFF will not be invertible. So you won't be able to calculate anything. And we want to make sure that for any physically reasonable system, all the eigenvalues of KFF should be greater than 0, okay? So this is a very important constraint that we should all any kind of reasonable system should follow. And if any of the eigenvalue is 0 or less than 0, we are going to say that the system is unstable. So I can replace this condition with less than or equal to 0 also. But 0 is typically, sometimes we write, okay, if it's 0 or less than 0, sometimes we just say it's 0. Both are equivalent way of stating that the system is unstable. To go over just some examples of what are the eigenvalues look like. For example, if I have an identity matrix of size n by n, the eigenvalues are just 1. So these are all the eigenvalues are all just 1. Okay. So in this case, you can see that determinant is actually multiplication of all 1. So determinant of this matrix is actually just 1. And we already know that determinant of identity matrix is 1. So this is a simple check that the ideas of eigenvalue is working. This is another example. It's a 2 by 2 matrix. And this matrix is actually, you can see that determinant of this matrix is 0. It's clearly singular. And if we calculate the eigenvalues of this matrix, eigenvalues are 0 and 4. And actually, you can multiply 0 and 4. That gives you 0. So determinant of A is actually 0, and A is actually singular matrix. So this is just to show you quickly how the ideas of this eigenvalues works out. Now, actually, we want to apply this idea to some kind of like a problems that we encounter in our class. So to illustrate the idea of eigenvalues, so here is a system we are considering. So this is the first example in which it's like a truss system. So we have 2 members, and I have actually at the point C, I have introduced a spring, and the spring stiffness is K sub S. So this is the spring stiffness. The member properties are given to us. This is for member A, B, and AC. But the spring stiffness property, Ks, we are going to specify later on. Okay, so let's assume that we're going to put some number later on here. Just think about the support condition. So this is like a pin here. So this support cannot move in any direction. But there is a roller here. So support C can move horizontally. Okay. So these are the support conditions, and we want to analyze this system and understand the stability of the system. So if we move forward, the first step is we are going to discretize the system and assign the degrees of freedom. So here the nodes are as follows. So I have introduced like 4 nodes. This is one node, this is another node, this is another node, and this is another node. And the degrees of freedom are labeled, the free degrees of freedom are labeled first. So this is the first, this is 1 degree of freedom. This is 2 degree of freedom. They are both free degrees of freedom. This is the 3rd degree of freedom. This is also free. And then I have level 4, 5, 6, 7, and 8. So these are the 8 degrees of freedom in this structure. And now we want to assemble the system and see and understand the stability of the system. So this is the element stiffness matrix for member AB. Now all of you are familiar with how to get the element stiffness matrix. In this case, I'm calling this as node I, this is node J. So the degrees of freedom ordering is 5, 6, 1, 2, 5, 6, 1, 2. Theta is 45 degrees, and these are the entries for the stiffness matrix. For member BC, I'm calling this as node I, and this is node J. And the degree of freedom ordering is 3, 4, 1, 2. So it's like 3, 4, 1, 2. Theta is 135 degrees. So this orientation angle is 135 degrees. And these are the entries of the stiffness matrix KBC. Now we have to consider the 3rd element, that is the spring element. But spring element is actually very similar to a bar element. So we can think like this is like a bar element. And in this case, this is the I node, this is the J node. Theta is 0 degrees. And we can just assemble the stiffness matrix for the bar element. The ordering will be 3, 4, 7, 8. 3, 4, 7, 8. But instead of using EA by L as a bar element stiffness or as a truss element stiffness, we can just substitute EA by L by KS. So I am going to use the KS as a spring stiffness. That is that we have said that, okay, we are going to specify the value later on. So we put the KS here, and this is the stiffness of this element. And finally, this is the assembled KFF and PF. Okay, so in this case, you can think that US is 0 and POF is 0. So to find the solution, we just need KFF and PF. And finding the solutions means finding the unknown UF, and the UF is actually U1, U2, and U3. And you can see that KFF is, in this case, we have assembled in terms of KS. So we have not yet assigned any specific value to KS. And in the next slide, I'm going to put some numbers in KS to see what happens. But to just give you an idea what we are trying to do here is, let me go back, few slides back. So you can think that this is a system like that, like with a spring. And one thing is actually think like what's going to happen if KS is 0. So KS is 0 means there is no spring here. Okay, so this spring is not present. So what does it mean? That there's a roller support here, and this roller support is free to move in the horizontal direction. And if you think a little bit carefully, you can see that there is a problem with this kind of a structure, because it seems to be this roller can move, and there is nothing to resist this movement. So it seems like that it seems like that this is physically unstable structure, and we want to see, okay, what is the mathematical quantity that reflects this kind of instability? Okay, and as we already discussed in the previous slides, that mathematical concept is eigenvalues. So eigenvalue is a very important concept, and we'll see that this concept of instability will be reflected in the eigenvalues of KFF. So let's go forward. So in the first case, I'm assuming that KS is equal to 0. So KS, there is no spring. Okay. And for this case, I calculated the eigenvalues of KFF. So there are 3 eigenvalues. The first eigenvalue is 0. The next 2 eigenvalues are these numbers. So you can see that one of the eigenvalues is 0. It means that the determinant of KFF is 0. It means that KFF is singular and KFF, inverse of KFF does not exist. And by definition, we will consider this a kind of system as unstable. So this system is unstable and we cannot find any solution in this case. So this is a interesting example where you can see that how if we have a incorrect property or we put some number that is physically unreasonable, that is reflected in the eigenvalues of the system. In the case B, what I have considered, I put some kind of a reasonable value of Ks. So I put like 1000 kip per inch. And after putting this number, I again calculated the eigenvalues of KFF, and then I got these 3 eigenvalues. And you can see that all the eigenvalues in this case are nice. Nice in the sense that they are all greater than 0. Okay, none of them are 0 anymore. So in this case, determinant of KFF is not equal to 0, and we will be able to calculate the known displacements that are U1, U2, U3 is KFF inverse times PF. And we will get this answer here. So we will have this answer. And because all the eigenvalues of KFF are greater than 0, we are going to call this system as stable. So the system is stable as all the eigenvalues are greater than 0. So this is the key concept. If any of the eigenvalues is 0 or less than 0, we are going to call the system as unstable. Otherwise, we're going to call that system as stable. Now, let me also illustrate you another interesting concept. What happens if we put Ks as a negative number? Okay, so you will think that, oh, I have not done a case where the eigenvalue is negative, but it can happen. For example, what I'm going to do is I'm going to put a Ks of negative 1000. So you can think like this as a typo. For example, you're making a code or you are inputting some values in your structure, and instead of putting a positive entry for the stiffness coefficient, you end up putting the negative entry in the stiffness coefficient. So in this case, if you try to calculate the eigenvalues of KFF, you will see that these are the 3 eigenvalues. The first eigenvalue is actually negative. Okay. Now you can see that one of the eigenvalues is actually negative, and but none of the eigenvalues is 0. So determinant is still not equal to 0. So determinant of KFF is not equal to 0, and you will be able to calculate some displacement. So because KFF inverse exists, and there is an answer here. So this is the answer. But this is not the answer we are looking for, because in this case, the system inherently is unstable, because we already decided that if any of the eigenvalues is less than or equal to 0, we are going to call the system as unstable. So this system is actually unstable, and instability is because of this negative eigenvalue, and this is because we have fundamentally made a mistake and put a negative value for the stiffness coefficient. So eigenvalues are actually, they reflect the stability of the system, and in any kind of reasonable structure, all eigenvalues of KFF should always be greater than 0. So a 0 or negative eigenvalue reflects instability. So this is an important concept, okay? And you can think that, if you think very carefully, this kind of stability cannot be detected by the inverse of KFF, because you will think that, oh, determinant of KFF tells us whether the system is unstable or not. But that's not true. For example, in this case, we can see that determinant is not equal to 0, but the system is still unstable. So the fundamental concept of instability is actually described by the eigenvalues. So always remember, eigenvalue tells us whether the system is stable or not. And to show you how these eigenvalues are calculated, let me show you a simple MATLAB script. And this script is actually available on Sakai, so you can go on Sakai and play with it. So let me show you the 3 cases. So this was the case A. Let me write case A. So case A was the case where the stiffness Ks was 0. And in this case, what I'm doing is I'm doing the stability analysis, means calculating the eigenvalues of KFF. So D is the matrix of eigenvalues and V is the matrix of eigenvectors. So I'm calculating both eigenvectors and eigenvalues. And I'm also trying to calculate the solution here. So in this case, PF was 20. So this is P1, P2, and P3. And UF is KFF inverse PF. So this is the solution. So let's see what happens if I try to do this calculation here. So I'm going to just run this script. And so let me show you my what the solutions look like. So you can see that my 3 eigenvectors. So V constitute 3 eigenvectors. 1, 2, 3. So there are 3 columns. These are 3 eigenvectors. The D is the diagonal matrix. So you can see that off diagonal entries are 0. And the first diagonal entry is actually, technically it should be 0. But because we are doing like a computation using finite digits, we get a very small number. So I will consider this small number as a 0. So this is still, I'm thinking as a 0 eigenvalue. Okay, so this is just a numerical noise. So the first number is 0. The next 2 entries are greater than 0. So you can see that this system has one 0 eigenvalue, and we already know that determinant of KFF is 0. And so if we are trying to solve the system, the MATLAB is giving us a warning that that the matrix is singular to working precision. So we already know that this is going to happen. And of course, we cannot calculate any U in this case because the matrix is singular. So this is the result I got on my system. And interestingly, you might be able to get not the exact number that I'm getting here. Every system has a different kind of a processor and computing environment. So the number you will get might be slightly different. Don't worry about the number. Just think about if it's very small, this is technically 0 for any numerical purposes. And so the important concept is that if the eigenvalue is 0, one of the eigenvalues is 0, then the system is not invertible and we cannot get the answer. Let me do the case B here. Case B was where we put KS to be 1000. Let me just comment this line. So this is a reasonable number, and then we can solve the system again. So I'm doing this solution of the system again. You can see that in this case, these are the 3 eigenvectors. First eigenvector is in first column, second eigenvector is in the second column, third eigenvector is in the third column. And these are the 3 eigenvalues. So diagonal entries are the 3 eigenvalues. So this is the eigenvalue 1, eigenvalue 2, and eigenvalue 3. So lambda 1, lambda 2, lambda 3. And in this case, determinant is not equal to 0, and we are able to solve the system. So this is the solution here. So U1, U2, U3. So this is a nice system. Everything is okay, and the system is stable. And finally, the third case was case C. In this case, we put KS as negative 1000. So this is the KFF, and again, we are doing the same analysis. We are doing the eigen analysis or the stability analysis and then calculating the solution here. So let's do this thing. So I'm going to run the script again, and to show you the results, let me increase the size here. So you can see that these are the 3 eigenvectors, and these are the 3 eigenvalues. So first eigenvalue is negative, and that indicates instability. So this system is unstable because one of the eigenvalues is negative. Okay, and so eigenvalue analysis is a very fundamental process that can tell you whether the system is stable or not. And let me show you one interesting case, because we said that V is the eigenvector. So actually, you can think like if you multiply KFF times V. So what I'm trying to do is, let me show you here. Let me clean this. So what I'm trying to do here is, because the first column is eigenvalue, you can say that KFF times V. I'm taking the first column and multiplying this minus V11 times V. So this calculation, so what I'm trying to do here is KFF times the first eigenvector minus eigenvalue times eigenvector. This should be equal to 0 because that's what the meaning of eigenvalues and eigenvectors are. So if we do this calculation, you can see that we are getting an answer that is very close to 0. So technically, these are very small numbers. So they're all 0 for any kind of numerical purposes. So this is, and this will also happen for the, if we check the second eigenvalue and the second, so I can put 2 here and 2 here. So you can still see that the solution, so this calculation is coming out to be 0 here, and so on and so forth. So all these eigenvalues and eigenvectors are eigenpairs, okay? And they satisfy the fundamental equation. So again, let me tell you why they're 0 here. If I go back to this slide, so you can see that what the calculation I was doing was like this. So actually, I was just writing a v minus lambda v. So a v minus lambda v has to be 0 if lambda and v are the eigenvalues and eigenvectors for the given problem. Okay, so I was just doing a v minus lambda v, and that turns out to be 0. So this tells us that our calculations are correct. So let me move forward, and let me do one more interesting example. But before doing this example, I want to go over the important concepts, especially related to the physical interpretation. How do we physically interpret the results? So as I already said earlier, that stability is actually closely related to the eigenvalues of KFF. Okay, so you want to make sure that the system is nice. All KFF are greater than, all the eigenvalues of KFF are greater than 0. And if you find that any of the eigenvalues is less than or equal to 0, then there are many things that you have to check actually. So you have to go back and see what's happening. What is the problem with the system? So one of the things that you want to check is probably check the support conditions. So you want to make sure that the structure is properly supported, so it's not moving as a rigid body. Sometimes you also want to check if the material properties are right. For example, modulus of elasticity should be greater than 0, area should be greater than 0, and so on and so forth, because we can easily make a mistake and put a negative number for these things, and then it will create problems with the stability. And sometimes actually you might also have to see that the system has enough elements. Actually, I will do an example to show you this idea. But what can happen if the system does not have enough members? Then there can be some internal rigid body modes. So a structure internally can deform as a rigid body, and that will create instability problems. So the system can become unstable just because some of the members, not the structure as a whole, but some part of the structure can move as a rigid body. Okay, so this is important that this should not happen. And so these are the checks that you want to do if you find any of the eigenvalue is less than or equal to 0. And so this is to give you a fundamental intuition like how to check the system. And finally, this is the interpretation of actually the eigenvalues, but there is also the interpretation of eigenvectors. So let me give you some physical interpretation of eigenvectors. So in general, we can think that this is the fundamental equation that we are always solving. We have PF is equal to KFF times UF plus KFS US plus POF. So this is the system that we try to solve when we are looking to find UF. Okay, so in this case now what we are going to assume that let's assume that US and POF are 0. So we are going to assume that US and POF are 0, and then we can simplify the system as PF is equal to KFF times UF. So this is just to simplify the ideas here. So this is the simple equation that I'm just simplifying this to this relationship. And now the idea is as follows. So what we're going to do is let's do one thing. So we're going to put some UF values, and we want to calculate PF. And the idea of stability is as follows. So what we want to say that if the UF is given, that is non-zero. So if we want to try to displace the structure, and that displacement is not equal to 0, then we expect that the PF we can calculate is KFF times UF. That should not be equal to 0. Okay, so this is the physical condition for stability. So what we are trying to say is, again, let me again repeat myself. If you're trying to displace the structure in some mode, you expect that the corresponding load is not 0. Okay, so it means that whenever you want to displace the structure, you have to apply some load. Okay, and this idea is reflected in stability. And actually, we can interpret the eigenvectors also if we try to think in this way. So let me give you an idea how to think about eigenvectors. Now let's suppose that lambda is equal to 0 is an eigenvalue of KFF. So the KFF is given and lambda is equal to 0 is one of the eigenvalues. So we already know that the system is unstable. And we are going to assume that V is the corresponding eigenmode. So V is the eigenmode corresponding to this lambda is equal to 0. And then what we are going to do is we're going to take UF is equal to V. So we are saying that, okay, the structure is going to displace in the eigenmode corresponding to the 0 eigenvalue. And then we want to calculate how much is the force required if we want to displace a structure in this eigenmode. So we are going to do the calculation like PF is the load required is KFF times the displacement. Displacement UF is now V. So this is the eigenmode. So KFF times V is equal to lambda times V because it's an eigenvalue, it's an eigenvector of KF or eigenmode of KF. So it's just lambda times V. And lambda is 0 because we are assuming that this is the 0 eigenvalue. So the load is actually 0. So it's very interesting. So what we are trying to say is if the structure is trying to move in this eigenmode, then the load applied for this kind of displacement is 0. And actually, this kind of eigenmode, sometimes we call it a rigid body mode. So it means that the structure is moving as a rigid body. And when structure moves as a rigid body, there is no load that is needed to deform in that mode. And again, this is related to instability. And we will think that, okay, the structure is unstable. And so you can think in the reverse way also for a stable structure. So if you have a stable structure, all the lambda will be greater than 0. And all the eigenmodes will correspond to a case where PF will be not equal to 0. Okay, so whenever you try to displace in a particular eigenmode that is related to a eigenvalue that is not equal to 0 or that is greater than 0, you will have PF that is not equal to 0. And so the main idea is for a stable structure, all eigenmodes should induce strains or forces. Okay, so all eigenmode should be able to create the strains within the structure. And we will see this idea in one of the examples. Okay, that will make this idea more clear. But this gives us the physical interpretation of the eigenmode or eigenvectors. And we are going to again use this in a more interesting example. So here's the example that I want to go through. And this is an interesting example in the sense that you can see that I'm doing something very weird in this example. So first of all, if you think carefully, there are two roller supports. Okay, so you can think that this structure is allowed to roll in the horizontal direction. So it's not supported correctly in the horizontal direction. So there is one intuitive idea that something is wrong with the system. And we want to see that what's going to happen if we do the stability analysis on the system. There's another interesting thing here that is going on. You can see that there's a node E at the center of this truss here at the top chord. And so there is a hinge here. So you can think that the member DE is connected here and EF is connected here. And there is no other member that is connected at E. So let's say that, for example, if I'm trying to apply a load at E, let's say if I apply a vertical load at E, this point is like free to move. This point or this hinge cannot resist that vertical load. Or if I apply a load at any inclination, it might not be able to resist. So there is something funny with the structure. And we want to see what are the eigenvalues, what are the eigenmodes, and try to make sense of what's happening. And the dimensions are given. So for each member, the dimensions are 15 feet, and the height is also 15 feet here. And the area of members is 2 inch square, and the modulus of elasticity of all members is 10,000 kips. So this data is given to us, and with this data, we want to analyze the system. And to analyze the system, this analysis is done in MATLAB. So I will show you a script in a moment how this is done. But let me show you the numbering of nodes and nodes and element numbers here. So I have labeled the nodes as this is the first node, this is the second node, this is the third node, fourth node, fifth node, sixth node. And there are like total 8 elements. So this is the first element, second element, third, fourth, fifth, sixth, seventh, eighth. And I have also labeled the degrees of freedom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 degrees of freedom in the system. And this analysis is done in MATLAB. Let me quickly show you the results first, and then I will discuss the MATLAB script. So this is the result for the system. So I'm also showing you the KFF portion of the stiffness matrix. So this is the KFF portion of the stiffness matrix. And finally, I calculated the eigenvalues of KFF. So you can see that the first 2 eigenvalues are like very small numbers. They are technically 0. So there are 2 0 eigenvalues in KFF. Clearly, this system is unstable. Okay. And we already know the determinant of KFF is going to be 0 because there are 2 0 eigenvalues, and we cannot actually take the inverse of KFF. So this system is unstable. And now what I'm going to do is I'm going to plot those eigenmodes. So let me show you the eigenmodes corresponding to the first 3 eigenvalues. So I'm going to plot the eigenmodes corresponding to the first eigenvalue, second eigenvalue, and the third eigenvalue. Okay, you can see that the third eigenvalue is actually positive. So this is okay. The first 2 are troubling cases. So this is the eigenmode first. So you can see that the black is the initial configuration, and the red line is the eigenmode. So this is the deformation in that eigenmode. Okay. So it's a deformation in the mode V1. So V1 is the eigenmode corresponding to the first eigenvalue. And clearly you can see that in this case, the structure as a whole is moving as a rigid body, okay? And because, as I told you, because lambda 1 is actually, technically it's a 0, but it's a small number here, so it's a 0. So it means that the PF is 0, because PF is KFF times the first eigenmode, as lambda times the first eigenmode, but lambda 1 is going to be 0, so technically it's 0. And this is a rigid body mode, and this indicates instability. So this is this 0 eigenvalue manifests itself as the rigid body mode, and so this is the physical meaning of what is the eigenmode. Similarly, I have plotted the eigenmode number 2. That also corresponds to the 0 eigenvalue. So this is also a very small number. Lambda 2 is a very small number. Technically, it should be 0, but this is just numerical noise. And you can see that the system is still moving as a rigid body. So you can see that in this case, this just moved vertically up, but this is like a rigid body motion, okay? And this motion is not creating any strains in any of the members. So the whole system is still moving as a rigid body. And finally, I'm going to show you the third mode, this corresponding to lambda 3 that is greater than 0. And now this is the deformed shape in the eigenmode 3. And you can see that in this case, the elements are actually deforming. So this case, the PF is actually not equal to 0. So PF is actually some reasonable number. So this is a strain-inducing mode. So the mode number 3 is correct. The first 2 are the modes that are creating instability in the system. Now the question is, how can we fix this kind of instability? So we start from here. So this was the case here. So the question is, we have 2 unstable modes, and how do we fix it? And the idea comes from, we can look at what are the unstable modes, and then we can think about fixing them. So there are many ways to fix them. For example, we know that the system is moving as a rigid body because I'm not supporting it correctly. So one way to fix is the system is actually to make, for example, this support condition at C. So I can remove the roller and make it fixed in both degrees of freedom. So one way to fix is change the support condition. So I changed the support condition here. I made it fixed here. So I'm fixing the both degrees of freedom at C here. Okay. And now I again want to do the same analysis. So nothing else has changed. I just changed the degrees of freedom, or sorry, the support condition at C. And finally, these are the degrees of freedom and element and node numbering. It's the same. Nothing has changed here. And this is the new KFF for the new structure. And these are all the eigenvalues. It's very interesting. Still, we have one eigenvalue that is 0 or very close to 0. So the first eigenvalue is 0. This system is still unstable. And you can check that a determinant of KFF is going to be 0. So this system is not invertible. So we still have some issues here. And actually, you have a pretty good idea on now what is the issue is. So if we try to plot the first eigenmode, this is the first eigenmode. So you can see that in this first eigenmode, the structure can still move as a rigid body. So this is like this motion is like a rigid body motion here. And in this motion, there is no force that is required. So there is this kind of stability. Sometimes we call it an internal stability. Okay. So because this is related to, because we don't have enough members that are connected to this node at this node here. So this is sometimes we think as an internal stability. And if we look at the second mode in this system, second mode actually corresponding to lambda 2 that is greater than 0. And this is a strain inducing mode. Okay. So this is okay. This is correct. So this makes physical sense, correct physical sense, and this is fine. The first mode is giving us a problem. So we can go back and we can think about how to fix this case. Now, there are many ways to fix this case. For example, we can add member like E. We can add a member from E to B. This is one way to fix it. Or we can connect from C to E. This is another way to fix it. So there are many ways to fix it. And so I'm just going to choose one of the solutions. For example, we can connect from A to E and like put an additional member from A to E, and that's also going to fix it. So there's not one solution to fix it. There are many solutions. So what I'm going to do is I'm going to put an additional member from A to E to fix this case, okay? Or to fix this, to improve the stability of the system. So let me go forward. So we can add different kind of members. So here I'm going to add one member that goes from A to E. And I'm hoping that this is able to fix the problem of stability in this system. So let's see what's going to happen here. Again, degrees of freedom, node numbering, nothing have changed here. And this is the new KFF, and these are the eigenvalues. Now, interestingly, all the eigenvalues are greater than 0. So there is no eigenvalue that is less than or equal to 0. So all eigenvalues are greater than 0, and this system is stable. And for this case, you can think that determinant of KFF is also greater than 0. So KFF is also invertible, okay? So KFF is invertible, and there is no issue with this KFF. And now if we want to see what is the eigenmode corresponding to the first eigenvalue, we can plot it. So this is the eigenmode corresponding to the first eigenvalue that is greater than 0. And we can see that this is a strain-inducing mode. So the first eigenmode is a stable mode. And actually, all the eigenmodes in the system are stable mode. And this system is perfectly stable. And this is what we want for any kind of realistic system. And this was the last case that I want to show in this example. Now what I want to do is I want to go back and show you how this is done in MATLAB. So in the MATLAB, I'm going to provide you these files. The first three files are the function files. They are already provided to you and they're used in the last lecture. But I have created two scripts. One is the truss example that we just went through, and this is the main script for stability. And this is the script I will provide to you. It will be available on Sakai for you to go through and understand how the script is working. This is pretty straightforward, but I again want to go through it. And this is actually based on our last lecture. So most of the script is similar to what we have discussed in the last lecture. And there are only few changes, and the changes are related to stability. And the changes goes as follows. So what we are trying to do here is, so this is the system we are trying to build here. And you can see that there are 6 nodes, 8 elements, and so on and so forth. So I have to define this geometric data here. So if I go back to my problem here, so there are number of elements are 8 here. So NELER 8, number of nodes are 6. And this is the coordinates. So I've defined the coordinates for every node. And this is 12 is to connect or to convert from feet to inches. And this is the connectivity. So I have 8 members, 1, 2, 3, 4, 5, 6, 7, 8. And the connectivity is defined as follows. The first member is between 1 and 2. The second member is between 2 and 3. The third member is between 4 and 5. Fourth member is between 5 and 6. Fifth member is between 1 and 4. Sixth member is between 2 and 4. Seventh member is between 2 and 6. And the eighth member is between 3 and 6. So these numbers are defined here. Okay. So you have to choose one order of connectivity, and that's okay. Finally, this is the DOF information. We don't have to change anything from the last class we have discussed. Nothing changes here. And next, I have to define the support conditions. So here, for this case, in the first case, the only 2 degrees of freedom are supported. The 2 is supported, and the 6th degree of freedom is supported. So I'm putting the index of supported degree of freedom as 2 and 6. There is no loads, okay? There are no loads applied. We are not solving the system. We are just investigating the stability of the system. So we are not solving any displacements or anything. So we are just trying to investigate the stability of the system. So there is no loads applied in this case. So loads are all 0. We don't need them actually. Finally, this is the data for area. So all the areas are 2 inches. All the E are like 10,000 KSI. So this is the value of E, alpha, DT, DL. They are not needed, so but they're just there. And finally, I can put a breakpoint here and try to plot the geometry just to check. So you can see that this is the geometry of the structure, and there is no issues. This means that the geometry is okay. And I can close it after this. And in this loop, we are assembling the global stiffness matrix. There is nothing new here. We are following the same idea that we discussed in the last lecture. And I'm going to put a next breakpoint after the assembly is completed. So, okay. So after the assembly is completed, we are just taking the KFF portion of the KG. KG is the global stiffness matrix, okay? So if you think KG, the size of KG is actually 12 by 12 because there are 12 degrees of freedom. But we are just taking the KFF portion. So KFF is, I'm just extracting using slicing. So I have the 3 degrees of freedom, IDF, IDF. So KG, IDF, IDF gives us KFF. So this is the KFF portion of the matrix. And then we are doing the stability analysis. Stability analysis means eigenvalue analysis. So here's the eigenvalue analysis. We are calculating both V and D. So I'm putting another big point here, and this is the V and D. So again, let me show you what V and D looks like. So let's see the D. So this is the D matrix. You can see that D is the diagonal matrix. Off diagonal entries are 0. And the diagonal entries are actually the eigenvalues. and the first two entries are, if you see that they're very close to 0, or they're technically 0. So in this case, the two eigenvalues are 0. And rest of the eigenvalues are all positive. So they're all nice. Let me close this and let me show you the V matrix. So if you see the V matrix, these are the eigenvectors. Okay, so these are the eigenvectors. And so they are like 10 eigenvectors, because the KFF size is, the size of KFF is 10 by 10. So it's there are 10 eigenvectors. Let me close this here. And finally, I'm just plotting those eigenmodes. So what I'm saying that to plot the kth eigenmode, so I can choose k is equal to 1 to 10, whatever number I want. And then I'm just saying UIDF is equal to the kth mode. So I am just choosing the kth column from that V matrix. And this is how I can plot the kth mode for the structure. And these are the magnification. I'm using a magnification factor of 10 in this case. You can change it. It depends on your problem. Just look at it. If you see the nice deformed shape, that's the magnification factor you want to use. And the deform flag is 1. And let me just show you what this looks like. So this is the first. So this is the first eigenmode. You can see that this is just a rigid body translation in the horizontal direction. And I can go and plot the second. So this is the second. I changed the k is equal to 1 to k is equal to 2. And I'm going to just solve this block here. And this is the second eigenmode. You can see this was the, again, a rigid body motion. This is the internal stability. This is the second mode. And I can say k is equal to 3 and plot the third mode. The third mode corresponds to the case where it induces the strains. So this is corresponding to the case where eigenvalue is greater than 0. And let me increase the magnification factor a little bit. Let's say to 20, just to show you a little bit better. So you can see that in this case, the structure moves, and there's a deformation in the structure. So this is a correct mode. This is a strain-inducing mode. And actually, we can choose any other mode. For example, if I check the 8th mode and plot that mode, this will also be a strain-inducing mode. So you can see that, OK, in this mode also, the structure has actually some strains. OK, so all the higher modes, like from 3rd to 10th, they will be all strain-inducing modes, and so on and so forth. So this was the first case where there were two eigenvalues that were 0. And then if we want to change the support conditions, we can easily do it in the code. So you can see that this was the new support conditions we used. So what we want to do is, in this case, it's supported for 5, 6, and 2. So there is another supported degree of freedom that is 5. So you can see that this is a very simple check. What we can do is we can go to the IDS and include the 5, because we're saying that 5 is also supported. OK, so 5 is also supported. So this is our second case where we have 3 supported degrees of freedom, and we can still do the stability check. So let's do the stability check, and let me plot the first mode. I'm going to run the entire code again to see what the first mode looks like. And you can see that the first mode still has that internal stability. So this is still a rigid body mode here. So because we know that the first mode corresponds to the 0 eigenvalue, if I see the D matrix, the first value is actually a very small number. So D11 is actually the first eigenvalue is still 0. So the structure is still unstable. So this is not stable. So, but if we check the second mode, in this case, you can see that this is a strain-inducing mode. So second mode corresponds to the strain-inducing mode, and so on and so forth. So third mode will also be the strain-inducing mode. And we can plot the other higher modes if necessary, but you got the idea. We just have to check the first initial modes to make sure that those are stable. The higher modes are always stable. And the last case is actually then we try to add an element here. So then we try to add an element here and to improve the stability of the system. And so we have to add one more element. So it means that we have to change the system. So in this case, we are adding the element between 1 and 5. And total number of elements will become from 8 to 9. So I have to change something in the code. Let me go back to the code and change things here. So first of all, I have to make sure I change the number of elements. So number of elements are 9. So I put NELE 9. And then I increased one more connectivity. I have to tell the connectivity of the new element. It should be, I'm saying this element is between 1 and 5. So I'm just going to put 1 and 5. So the last element is between 1 and 5. So this is our new element. And this is done. So we are done. And then support conditions are still 2, 5, 6. So you can go back and you can see that still 2, 5, and 6 are supported. And we want to check the stability of this system. We do the same exercise. Let me plot what the first mode looks like. After getting after doing the stability analysis, let's plot the first mode. And this is what the first mode looks like. And you can see that this is a strain-inducing mode. And in this case, none of the part of the structure is moving as a rigid body. And so this is a stable system now. And finally, actually, we can check the higher modes also. Let me check the second mode here. And you can see that this is also stable. So this is also a strain-inducing mode. All the higher modes are stable because they are associated with eigenvalues that are greater than 0. Okay, so that's an important check here. And let me show you the D or the eigenvalues. You can see that all the eigenvalues are all nice and positive, and none of them are 0. Off-diagonal entries are 0, so don't worry about them. Only the diagonal entries are the eigenvalues. Okay, so this is lambda 1, lambda 2, lambda 3, and so on and so forth. And so these are the results I presented to you on the slides. But actually, there are other interesting things you can do. For example, you can add, let's say if we want to add one more element that goes from 3 to 5, what's going to happen? Actually, the system will still remain stable. So everything is going to be still nice. So we can add it easily. So let's say that what we can do is we are going to increase one more element to, let's say, NELE is 10. And we want to increase one more element. That element goes from 3 to 5. So I can just put I node is 3 and J node is 5. And we just want to see what is the first, we still want to see the first eigenmode for this case. And so this is the first eigenmode. And actually, this is a strain-inducing mode. And because it is associated, if I look at the eigenvalue is still positive. The first eigenvalue is positive. All the others are also positive. So the system is stable. And there is no eigenvalue that is 0, so or less than 0. So we are good here. So you can see that there's not just one unique way to make the system stable. There are many ways that you can think about. But eigenvalue is a very important check to understand the stability of the system. And this concludes the numerical exercise for this class. And actually, I'm going to put this code on Sakai, so you can go through this code and try to understand the things yourself. And as always, if you have any questions, let me know. And I again just want to mention one thing. You might have, if some of you have taken dynamics, you might have heard this term eigenmode. The eigenvalue analysis that we are doing is a little bit different than what you do in dynamics. Okay, but the concepts are very similar. So don't confuse these eigenmodes as the one that you learn in dynamics. So you can think that these eigenmodes are for stability, and when we use the eigenmodes in dynamics, those are for different reasons. So let's not confuse them together, but you can learn these concepts separately. But the ideas of eigenvalue analysis are very fundamental, and they're both applicable in dynamics and also in stability of structures. So here we are using for stability. It can be used for dynamics, and actually it can be used for many other things. So right now the application is stability, and To conclude, always remember that for a stable system, all the eigenvalues should be greater than 0, and the corresponding eigenvectors should be strain inducing. Okay, so those are not corresponding to a rigid body mode. And whenever you have eigenvalue that is 0, that will actually correspond to a eigenmode that will displace a structure in a rigid body mode. And the rigid body modes can be both global, so globally the structure can move as a rigid body, and can be a local, so only a part of the structure can move as a rigid body. Okay, and both of these things should not be present in any kind of